It happens so much faster than you think. You're on a deadline, you're trying to test something, and maybe you just drop a temporary database password into a config file.
For just a second.
For just a second. You hit commit, and then you realize, oh no, and you immediately delete the line, push the fix. You think you're safe.
Right.
Problem solved.
But it's not. That secret, that credential, it's now basically a permanent part of your repository's history. It's just lurking there, waiting for someone or some script to find it.
And that is the absolute core security challenge with modern version control, isn't it? You can't just delete something from Git. I mean, not really. You have to rewrite history, it's messy, it's complicated.
And that's exactly what we're getting into today. We're diving into the source material you provided, a really detailed readme for a tool called Git Secret Scanner.
Yeah, and this tool is built specifically to deal with that exact problem, that deep historical security debt that, frankly, most standard security checks are going to miss entirely. So our mission today is to really unpack this thing. It's a full stack application, and it's designed to be this comprehensive net scanning Git repos for exposed secrets, tokens, you name it. We don't just want to know what it finds, we need to understand how it finds it at a depth that, like you said, a surface level scan just can't match.
And our goal for you, the listener, is to really understand that effective secret scanning, it requires chronological depth. It's not a snapshot in time.
Right.
This tool makes a very unique promise. It says full history analysis.
Yeah.
We really need to spend some time on what that means, because that promise is what separates a basic audit from a real forensic security investigation.
Oh, okay, let's unpack that then, because if your goal is just to find secrets, most people would just, run a simple file scan on the latest code. What makes this scanner so much more powerful?
It's all about the scope of the search. I mean, the source material points to two features that are absolutely non-negotiable for a really thorough audit. First, it automatically finds and scans every single branch in the repository. And second, it does that full history analysis we just mentioned. It scans the entire Git commit history, not just what's at the current tip or head.
Okay, scanning all branches, I get that immediately. Old feature branches, stale dev branches. They're always forgotten, but they have old, sensitive test configs all over them.
Exactly.
But scanning the entire history? I mean, that just sounds computationally brutal. It sounds so slow.
It is, and that's precisely why that feature is so critical. Just think about the implications for a second. A secret gets committed a year ago, it's deleted 3 days later, and then the branch it was on gets merged and deleted.
Right, gone.
I think it's gone. But that secret is still completely extractable by an attacker who knows how to dig into the repository's objects. If you don't scan the history, you have these massive, massive blind spots.
So an attacker doesn't care about the current state of your code?
Not at all. They care about the most vulnerable state it has ever been in, even for a moment.
So you're saying secrets from years ago could just be sitting there, recoverable with standard Git commands, and this tool is like a digital archaeologist, designed to go find them across all branches and the entire commit history.
That's a great way to put it. And that, of course, brings us to efficiency. Because if this analysis takes hours and hours, no security team is ever going to use it.
Of course not.
The sources address this directly. They describe the tool as fast and efficient, and they mention it uses background processing with real-time progress updates.
Okay, so that engineering choice is key. That makes this powerful feature actually feasible. How does that background processing work when you're dealing with huge repositories?
Well, it suggests a design that's really optimized for parallelism and I/O. I mean, cloning a massive repo and then walking through tens of thousands of commits, that's an I/O heavy task.
For sure.
So by delegating that to background processes, the scanner could just sort of chug through the history without ever locking up the UI. It turns what would be a massive bottleneck into a simple background task.
Which means it's actually practical for a real company to use.
Exactly. Efficiency ensures adoption.
Okay, so efficiency makes it usable. We know how deep it digs. Let's talk about what it's actually looking for. It has to be more than just simple keywords, right?
Oh, absolutely. This is where you move from just forensic analysis to highly specialized pattern recognition. The source material says the scanner can detect 50 plus secret patterns.
50 plus.
Yeah, and what that implies is a really structured database of regular expressions, all tailored for very specific, sensitive data formats.
That's a huge number. It feels like it covers pretty much every digital access point you can think of. Let's try to organize this for the listener based on the sources categories. starting with the highest risk.
Right. The highest risk is always going to be cloud provider keys.
Yeah.
We're talking about credentials that can grant you like near total infrastructure access.
So AWS access keys, Azure storage keys.
Yep. GCP API keys. These are almost always critical severity because one exposed key can lead to immediate massive compromise.
Okay, then you've got the huge world of API tokens. These are the credentials for all the services developers use every day.
Right. And the list is long. The source mentions GitHub, Slack, Stripe for payments, SendGrid for emails, Twilio, Discord tokens.
And we should probably just touch on the risk here. I mean, a Slack token is serious, but it's not the same level of disaster as an AWS root key, is it?
No, not at all. It's a different scope of damage. But finding one still means an attacker can often impersonate a user or cause some serious operational disruption. It's still a big deal.
Next up, the source lists private keys. Now, this is different from an API token. These keys often represent like identity or the ability to sign things cryptographically.
Exactly. And the tool looks for specific types. RSA, OpenSSH, DSA, EC, and even PGP private keys.
And the risks there are fundamental. An exposed OpenSSH key means an attacker can just log into a server as you.
Right. An exposed PGP key can let an attacker sign commits or messages, completely breaking the chain of trust in a secure workflow. That's why these are almost always critical or high-severity findings.
And finally, what most applications run on: database credentials.
Yep. Connection strings for MongoDB, PostgreSQL, MySQL, Redis. If you expose these, your data itself is gone. User data, financial records, everything.
And the last category is just generic secrets.
Which is a catch-all for standard passwords, general API keys, and importantly, JSON Web Tokens, or JWTs. And for you, the listener, it's worth remembering that an exposed JWT can allow for immediate session hijacking if it hasn't expired.
So we're talking about scanning for highly specific structural identifiers, not just looking for a string that says password.
Precisely.
Okay, so that depth of pattern matching is great, but detection is only half the battle. If you find 100 potential secrets, you have to know which one to panic about first. How does the scanner turn all that raw data into something actionable?
And that brings us to the results and the user experience. This is where the tool goes from just being a scanner to being a true risk assessment platform. It does this with its severity classification system. The system breaks down every finding into one of 4 levels, which basically forces you to prioritize your cleanup based on the immediate impact.
So let's run a scenario. A dev team runs a scan on an old project, and they get, say, 52 results. How does the system guide them?
It immediately points them to the top tier, critical findings. These are defined as credentials that lead to immediate, broad system compromise. So those AWS keys we mentioned, or the private keys.
So if they find one critical key, they stop everything else.
Stop everything. Revoke that key first, then you move down the list.
Next is high severity. So that's API keys and tokens with significant access, but maybe not total infrastructure control.
Exactly. Maybe a key to a payment provider. Still an emergency, but a more contained one. Then you have medium, which covers tokens with limited scope, or what the source calls publishable keys.
And finally, low severity for things that are maybe sensitive but have a pretty low direct risk. This whole structure is what makes the tool so valuable. It's a roadmap for what to fix.
It is. It provides a direct map for where to put your resources first.
Now, what about actually using it? The source describes the UI as a beautiful cyberpunk-themed dark interface, which is catering to the audience, I guess.
It definitely is. But it implies this isn't just some clunky command line tool. It's designed to feel powerful and engaging while you're looking at this dense data.
Right, so visualization matters. But if the team just found a critical AWS key, the auditor is now looking at a live, dangerous secret on their screen. What protects the user from that?
And that leads to a crucial safety feature, safe masking. Secrets are automatically masked in the output.
Oh, that's smart.
It is. The user can see where the secret was, who committed it, and its severity, but the raw confidential string is hidden. This protects the person viewing the results from accidental exposure, from copy-paste errors, or from showing it on a shared screen. A simple detail, but absolutely vital.
Okay, let's switch gears and go under the hood. For someone listening who wants to deploy this system, what are the bare minimum requirements to get it running?
So we are dealing with a full-stack app. You need a few things ready to go. On the prerequisite side, it's Python 3.9 plus with pip for the backend logic, Node.js 18 plus with NPM for the front end, and of course, Git installed and available in your system path.
And architecturally, the source diagram shows a really clean split, right? It's a React front end and a FastAPI backend. We should justify that split, though. Why use React and Node for the front and then FastAPI and Python for the back?
That split is really driven by the task itself. React gives you that snappy, modern UI they described. But the backend needs raw speed and power for the heavy computation.
Right, for the history analysis.
Exactly. Python is excellent for that kind of complex graph traversal and pattern matching. And FastAPI is a great asynchronous framework for all the I/O-heavy work like cloning a repo while keeping the API endpoints fast.
That makes perfect sense. The front end stays responsive while the heavy lifting is delegated to the scalable Python engine. And since that scanning can take a while, the source even gives deployment recommendations.
Yes, it does. They suggest deploying the front end to a serverless platform like Vercel and running the compute-heavy backend on a service platform like Railway, though they do mention alternatives like Render or Fly.io.
Which shows this is built for persistent remote auditing, not just a one-off check on your laptop.
Right.
Now, what about customization? Let's say a security team needs to find a unique secret that's specific to their company, a proprietary license key format or something. Can they add to the built-in patterns?
Yeah, absolutely. And the source gives explicit instructions, which is key for adoption. You customize it by editing a list inside the core logic file, backend.app.py. But here's the crucial part. You don't just add a regular expression.
Right, because if you've built this whole sophisticated risk classification system, you have to use it.
You have to use it.
Right.
So to add a new pattern, you define three things. A name for it, the regex pattern itself, and critically, you have to assign it a severity level high, medium, or low. This ensures any custom patterns you add immediately get the benefit of that structured risk assessment.
This moves us into our final segment. And as we've said, this is a powerful tool. And with great power, well, the security notes section of the source material becomes maybe the most important part of the whole document.
You cannot skim this section. The authors give very, very strict guidance. First, the tool is for educational and authorized security testing purposes only. This is a bright red line.
So if you go and scan a public repository you don't own,
You are violating policy, potentially professional standards, and creating a huge legal and security risk for yourself. The ethical obligation is to only scan repositories you own or have explicit permission to audit. The authors are pushing that responsibility squarely onto the user.
and what about the results themselves? If you find a critical key, the last thing you want is that data being saved somewhere it shouldn't be.
The scanner addresses this with a core design choice. The results are stored in memory only. They are not persisted to disk.
That's a huge security feature. It prevents them from ending up in log files or temporary backups or system snapshots. Once the session is over, the sensitive findings are just gone from the tool itself.
It reinforces the investigative nature of the tool. It's meant to find the problem, show you the risk, and then gracefully forget the sensitive data. And the authors summarize all of this by saying they are not responsible for any misuse. That ethical obligation is paramount.
So we've shown how this application gives you a quick, thorough, and really granular view of security debt that's hidden deep inside a repo's history. It classifies that risk instantly. It really changes how you have to think about source code security. You have to look at the past, not just the present.
Indeed. We've shown why effective scanning has to look at every single version file, which brings us back to that foundational concept. If a secret can live forever in a repository's history, even after the file is gone, the scanner can only detect the problem.
Right, which raises an important question for you, the listener. If deleting a file doesn't actually delete the secret, the problem is still the history itself.
So what practical and frankly painful steps are truly required to irrevocably erase that history and keep that key from ever being recovered? The detection is fast, but the effective remediation rewriting and force pushing a clean Git history, that can be complicated, risky, and very time-consuming.
And that difficult process is the price you pay for not scanning frequently enough.
It really is.
A lot to think about the next time you hit Git commit and have that moment of panic. Thank you for sharing your sources for this deep dive.